Following is a video on experimental crack detection of metal using vibrothermography, presented in collaboration between the China University of Petroleum Center for Offshore Engineering and Safety Technology and the University of Houston Smart Materials and Structures Laboratory. Let's begin with an introduction to vibrothermography. Constructive testing is a critical method for examining structures or different types of equipment to ensure that it's safe. It allows us to examine the materials without actually taking them apart. One of the major NDT technologies is infrared thermography, which uses the thermal information of materials to detect defects. Some advantages of IR thermography are that it does not require surface contact, it has high testing efficiency, it can do real-time testing, and it is suitable for a wide range of materials. The three main aspects of thermography are that, firstly, any object with a temperature above 0 Kelvin will emit infrared radiation that can be captured on an IR camera. The second is that the areas of an object with different temperatures can be represented by the features of an IR image, i.e., the higher temperature, the more power the infrared radiation. And the last point is that the presence of defects can change the temperature distribution of tested objects due to different thermoconductivity. There are two kinds of thermography, according to the source of excitation heating. If heat excitation comes from the outside, it is called active thermography. Passive thermography uses internal heating as excitation. Vibrothermography is a kind of active thermography that uses ultrasonic or vibration waves for heat excitation. The mechanism in vibrothermography is a mechanical wave propagates across the surface. If there is a defect on the surface of the object, for example a crack, such a mechanical wave can cause friction. This friction will cause heat to be generated around the location of the crack, which can be detected using IR imaging. Compared to other NDT technologies, vibrothermography has many advantages, such as it is very fast to detect defects using vibrothermography, usually no more than a few seconds. In vibrothermography, the heat is generated selectively at the location of defects. It is easy to control and repeat experiments by changing certain parameters of excitation, and the cost is most economical. Next, we will cover the experiment. The experimental setup consists of primarily three parts: the vibration/ultrasonic excitation equipment, the IR camera, and computer. The excitation equipment includes the signal generator, piezo driver, and piezoelectric actuator. Shown are the IR camera and the piezoelectric stack actuator used for the experiments. The specimen used in the experiment is an aluminum bar with 3 cracks. Cracks 1 and 2 are vertical, whereas crack 3 is horizontal. Next we will cover the experimental results. The following is an experiment using vibrothermography for crack detection. The total time of the experiment is 20 seconds. We will start the ultrasonic excitations at the 5th second and stop them at the 15th. Let's begin the experiment. No excitation will occur in the first 5 seconds. The excitation starts, and you can see the cracks beginning to form in the video. The excitation will stop, and the cracks will no longer be detected. The following images show us a trend between how much excitation heating has occurred versus how clearly the crack can be seen through vibrothermography. The following is the temperature data set of 3 points at each crack. The temperature of the cracks rise about 0.5 to 1 degree Celsius over about 2 seconds when the ultrasonic excitation is introduced into the specimen. The amount of damage detection is proportional to the power of excitation. Too much power will be costly and may damage the specimen. Using the minimum amount of power required to acquire satisfactory results has become a major interest for researchers in recent years. Crack detection is extremely sensitive to whether the specimen is fixed or free. In this experiment, when the specimen is entirely fixed, crack detection improves. The major reason for this is that the mechanical wave can be more easily converted into heat when the specimen is entirely fixed. The frequency of excitation is key for defect detection in vibrothermography. If different frequencies are used, poor results will be obtained. Generally, we find a suitable excitation frequency via frequency sweeping. When the PCT actuator is farther away from the cracks, or on the opposite side of the specimen from the crack, good detection results are still obtained. Now we will cover the conclusion. It has been validated that vibrothermography can be an effective way for the detection of surface defects for metal parts. Still, there are many problems to be studied about it. The temperature increase due to vibration excitation is about 0.5 to 1 degree Celsius, and mainly appears only at the location of cracks. This contributes to how safe vibrothermography testing is. The power of excitation is crucial for the detection using vibrothermography. Currently, there is a lot of potential for using vibrothermography to detect all kinds of defects in a variety of materials. Techniques of effective detection with lower power of excitation would be key for further development in vibrothermography. Thank you for watching. We hope you enjoyed this video.